The mental. Anyway, so
yes, I'm hyped.
Intro to FTC. This is the intro. Nice thing is, for the AP, you don't have to know why. However, it would be a severe travesty if you never saw why FTC actually worked. It technically all comes back to a good old-fashioned MVT. Who's MVT?
Mean value theorem.
Mean value theorem. And what does mean value theorem say? Oh, some things got
There's an average rate of
raised.
change equal to the instantaneous or something or other. That's all. Except it kind of fell apart because some things are erased.
Yeah, something happened.
You know what time it is?
Still looking beautiful though, just saying.
Preach it.
There we go.
It's good enough.
X equals C equals, X star. Okay.
Is that actually like a quote from
Basically, MBT kind of applied to the statement that you see. So, first of all, before we get to MBT, at the very, very top, given X sub 1, X sub 2, X sub 3. Now, here's the strange thing. Technically, our book, and some of you have seen this notation, and even the AP sometimes, wouldn't even say X. Instead, our book would say C. Have you guys seen them using C's? Our book would use C's to be those special X values in between the X interval A to B. So technically, our book and many others named them C's instead of X's just because X is more general, C is a bit more specific. So one thing we can do is we can change these to C's just to make it more like what you might see with the limit definition of the Riemann sum. You see?
You're so cool, Sean.
Oh no, why are you little? Don't be little, be big. Aww.
I love it.
Okay, be big, there we go.
That's all I'm good for.
And then we could call it delta X, and could also call it delta C. We'll keep it delta X, so I think, and what I was noting and how our book was showing it, it made a little more sense that way. So, the only thing that would change is down here, technically we could call it C sub 1 instead of X sub 1. So I could go ahead and come over here and change it to be X equals C sub X star. I don't know, different ways of doing it. Some of the definitions use X star to be the special C, some places use the actual C to be the special guy. Anyway, long story short. We have these different C's in between A to B. And somehow, the C's are marking basically the heights that we're going to be using. For instance, it could be C sub 0, C sub 1, C sub 2, etc., all the way up to C sub n minus 1. We could use all of these ones for the left point approximation. We would leave off the left one. The far right one, the B. If we were doing a right-hand approximation, we'd use all of these guys to plug into f of x in order to do our Riemann sum approximations. Or they could literally just say, hey, these are the C's, you use them, you might not know who they are, left or right or midpoint. You're like, yes ma'am, yes sir, I don't know, yes Mr. Book. I'll go ahead and use those C's. But there still needs to be some sort of way of partitioning, of having delta x's for each of our bases, even if they choose these C's kind of irregularly. There we go. So the C's are what we use to plug in for the heights, and then the delta x's are the bases. Now, this is just saying, hey, you have an A to B, partition it. That's basically what it's saying. You have an A to B, partition it. Split it up. How many pieces? I don't know, n pieces. Let me get the exists back. If we have an interval A to B, and if we partition it, split it all up. And we remember MVT that says, hey, within an interval, as long as a function is continuous and differentiable, as long as a function is continuous and differentiable, and the ironic thing is, since we have an integrand, that means it's the derivative of someone, which means he had to have been continuous and differentiable, the original function that we're looking at. We can say that there exists an x equals c equals one of these special c substars. There is a special c within each interval such that the derivative will equal the average, or as Tyler was saying, the instantaneous equals the average. Just a quick reminder of MVT. There's a place where f prime, antiderivative prime, is equal to antiderivative of B minus, where did my capital F go? Minus antiderivative of A.
Oh.
That makes more sense. All over B minus A.
So what's the upside down E?
For all x. Sorry, just a shortcut way. For all x. So it's saying, okay, since there's a derivative being taken, that means that the original was differentiable. Capital F was differentiable. If it's differentiable, it's continuous. Therefore, it satisfies what we need for MBT. Therefore, we can find these special C stars such that. F prime of C sub 1 star, that would be the special C, times delta x sub 1 is going to equal F of, that's our first subinterval. Our first subinterval is going to have C1 minus F of A. And then for the next one, we could say for the second subinterval, we would have the second C star times the second delta x, whatever that might be. Now what I'm doing is I'm rearranging MVT. So I'm saying I can take that F prime of the x star times B minus A to equal F of B minus F of A. So I'm basically just rearranging MVT, multiplying the B minus A to the other side, realizing that B minus A is the delta x for every single subinterval. For the first subinterval, I have, I'm looking at it this way, a number line. There's A, there's B, here's C1, here's C2, here's C3, here's, well, C sub n minus 1. So the first subinterval, I'm saying, hey, I have these two guys. I can make this conclusion with these two guys as the A and B. So I'm like, okay, cool. So the special C star derivative times the delta x for that interval, whatever that length is. I'm going to use the F of C sub 1 minus F of A, using this little formula of take the antiderivative of the second minus the antiderivative of the first. And I can keep doing this. Then I have my F of C2 minus F of C1. For my third subinterval, I can keep doing this, and I'd have my third special C sub star guaranteed by my MVT, the place where the derivative will equal the average, times the delta x sub 3, which just denotes the B minus A of the average rate formula, equals the antiderivative of C sub 3 minus F of C sub 2. I could do my F prime of C sub n minus 2 times delta x of n minus 2 equals F of C sub n minus 2 minus F of, I apologize, it'd be the latter minus the former. I want to do n minus 1, not n minus 2. I'm being lazy, I don't want to write them all. Just do n minus 1. There we go. F of...
Yep.
Well, I did want n minus 2. F of C sub n minus 1. Then I want F prime of C sub n minus 1 star times delta x of n minus 1 equals F of C sub n minus 1 minus F of reached f of b. Whew. There we go. Nope, we have one more interval. C sub n minus 1. C sub n. I wrote something down.
Why is it n minus 2?
Oh, B is ladder.
Yeah. I thought B was like the higher. Am I thinking of this one? Oh, wait, yeah. Wait,
Oh, that would be n minus 3. That's awkward.
okay.
There we go. That makes sense, right? Higher and then lower?
Yeah.
There we go.
It wasn't
Low C and so, yeah. It wasn't matching up with the symmetry. It gets weird when you start having these like ambiguous ones.
And that's n
F of
minus
C n minus 2. Yeah,
And
yeah.
then
That's why I was messed up. I wrote it wrong.
2.
So we need one
So
more.
then,
We haven't gotten to F of B yet.
Oh, but how would you?
There we go. Now we've made it to F of B. Because F of B is the final C. So even though we were following the pattern, C sub n is the ending. So then even though I put C sub n, even though it is the nth subinterval, we can replace that with just F prime of, well, the problem is though, B is not necessarily the special inside. So what I'm trying to explain is on the very nth one, you're at the final partition, at the final boundary of your area. And so even though it is the nth special C in the nth subinterval, which would be this one down here, if that was the first, the second, the third, the fourth, etc., this is the nth. We're not going to use C sub n because that is the ending, which we already know to be B. And here's the weird thing. From all of these are, this is antiderivative prime, which is the same thing as the integral. Because remember, this little guy is who's in your integral. And it's the antiderivative prime, which equals that inside function. This is tying together how an integrand or an inside function is the derivative of somebody. Who is that somebody antiderivative? So all of these are really just function values at special C's, and function values times bases are heights times bases, and heights times bases, what are each and every one of these expressions? Little rectangles. Yeah. So I have bases times heights, and bases times heights, and bases times heights. And so if I was trying to find the total area, wouldn't I need to add all these together? And as I add all these together, kiddos, what if C sub n was, or n was 100? How many of these would I have? I'd have 100, but still, at the very beginning, even though I'd have C sub 1 and it would go to C sub 100, I would still end at B and I would still start at A, sure? Okay, what if I had 1,000 of these? I would have 1,000, but wouldn't I still start with F of A and end with F of B? What if I had 1,000,000? I would still start at F of A and end at F of B. What if I went to 1,000,000,000,000? Wait a minute, aren't I kind of approaching infinity? Okay, what happens even if I have 1,000,000 or 1,000,000,000? Look at what happens with this one. What's going to happen with, if I'm adding all of these up, in order to add all my rectangles up, using MBT, I add all of these differences of the antiderivative together. Do you guys see how F of C sub 1 is positive 1 second and negative the next? Ooh, so aren't those going to cancel? How about this guy? Isn't C sub, F of C sub 2 positive then negative? What about this guy? He's going to cancel with the next one. What about all the ones in between? They're all going to cancel. What about these guys? They're going to cancel. He would have canceled from up above. What about these guys? The infinite addition, or the addition of the infinitesimally thin rectangles, can be summarized or simplified to be F of B minus F of A, as we take the limit as n goes to infinity of the Riemann sum repeated addition. The Riemann sum repeated addition, I'll use I because that's what the book likes to use, of capital F prime of C sub I star times delta x sub I. Kiddos, who is this guy?
Integral.
definite integral from a to b of f of x dx is equal to the antiderivative of b minus the antiderivative of a by just a simple, maybe not so simple, but in some ways a simple application of the mean value theorem to n subintervals. Infinite addition and one subtraction. Infinite addition and one subtraction. Whether n was 10 or 100 or 1,000 or a million or a trillion, doesn't matter. This is one illustration, only one. I'm sure 3 blue, 1 brown would have a better way of explaining it. This is more of the mathematical proof, to some degree, of why the fundamental theorem of calculus is what it is. Now, technically, the fundamental theorem of calculus, there are 2 different parts to it, different books call different parts. One's part 1 and the other one's part 2. Long story short, they're both fundamental theorem of calculus. There's 2 different facets, just some people call the first the second and second the first, depending on chronological order or depending on the importance. It's weird. We already have 2 different cards. I'm going to establish a part 1, part 2. BC book actually flips it and makes the part 2 the part 1, the part 1 the part 2. What's important is that it's FTC. What's important is that it's FTC. So let's go ahead and take that big old blah and write down the most important part. The y is pretty stinking cool if you were able to follow it. The application, though, is a lot simpler. The application says, if a function f, lowercase f, aka the integrand, aka the little guy inside the integral, is continuous on, if it's not continuous, there is another way to deal with it. It's called an improper integral. You can ask your Calc BC kid, and they'll tell you how improper integrals work. Basically, we go back to limits. But for our purposes, as long as f is continuous on a closed interval, we can always say simply that the definite integral from a to b of f of x dx is equal to the antiderivative of b minus the antiderivative of a. And thankfully for you guys, you've seen me kind of introduce that a few different times. So it's the change in the antiderivative. So a quick reminder, even though you have your own forever card for the antiderivative, just a quick little reminder. Put it in parentheses. You don't necessarily have to memorize it with the card for a forever quiz. But remember, capital F is the guy whose derivative is inside the integral. Does that make sense? Capital F is the guy whose derivative is inside the integral. He's the OG. He's the guy that we're trying to find when we anti-derive. So, as you guys write down this, which is forever card 36. Okay, thanks. I thought so. We can start looking at the example down below and saying, why haven't we seen this guy before?
Not geometric.
He's not geometric. He's not a line. He's not a circle. Because a line would be mx plus b or some sort of constant. A circle would be?
Square root of r minus x squared.
To the power 2 over.
R to the power of 2 or r squared minus x to the power of 2 or x squared. Not geometric! Could we have approximated this with a Riemann sum and done A1, A2, A3 for n equals 100 and done like this whole splitting up into 100 different pieces, the area from 1 to 4? Yes. But we're not going to do that because we just learned, hey, the way to solve this exactly perfectly, the way our calculator would solve it, well, actually our calculator, the programming, doesn't know antiderivatives because it needs to be able to solve any integral that you could possibly give it, and not all integrals can be anti-derived. Your calculator actually uses an approximation technique in its programming, a really, really, really good one, but it does not solve it exactly. So we're going to do even what our calculator cannot. We're going to solve it the perfect way, and the perfect way says, can I anti-derive this guy? We have to find the antiderivative.
Yes.
Yeah, but we probably want to rewrite it first. Come on, we got to go back to section 4.1. Let's write this as, Tyler, x to the negative what?
1.5.
1.5 or 3/2 might be a little easier.
Oh, okay, yeah.
Why negative 3/2? Because isn't this x to the 1 and x to the 1/2? And what's 1 plus a half? Exponent rules. Common basis, just add. 1 plus a half is 1.5, which is 3/2. 2 over 2 plus 1 over 2, right? Why is it a negative? There's in the denominator, those people that are yawning. How do I do the power rule with x to the negative?
You got
You got a plus one, so it's
Add 1. So I'm going to add, if you need to see it, because it's been a while, I'm going to add 2 over 2, yeah? Cool. And then add that. That's negative 1/2. Don't I have to multiply by the reciprocal?
should I actually?
Ooh, and then plus c. Stink, this is messy.
Yeah, it's pretty
Okay, but pause. Power plus 1 divided by is multiplying by its reciprocal, right? So I end up with, well, hold on, wait a minute. Why did I draw this little bracket if there's no bracket anywhere else? Some books would also, and depending on the problem, I write it different ways.
And then do
Some books also do, or some teachers, professors, etc. use a straight line. I do that too sometimes. I need to put in the bounds and say, no, I'm not done yet. This is not just an antiderivative. It's not just an indefinite integral where I find a function and I'm done. I need to find a number. I need to find that area that's represented. How do I do it? I say, here's the antiderivative. Here's the capital F. Not F prime, that's that guy. So here's the capital F. Now I need to plug in B, then plug in A. Plug in B and then plug in A. F of B minus F of A. Bob minus Bob, I don't know. Some way of remembering it. F of B minus F of A. Top minus bottom. I gotta plug in the 4, then plug in the 1. Now how many of you guys want to plug in right this second? That's
I don't see why not.
How about, can I just do negative 2 over, isn't it going to be x to the negative 1/2 or square root of x? Isn't that a little bit easier to like mentally process? I think so. Maybe if you don't, then you're super cool. But anyway, when we plug in, I have to plug in the b, plug in the 4, so just think the top goes down, then we bring in the 1. Top down, bring in the 1. So we have negative 2 all over square root of 1 plus c, f of b, the whole shebang, minus f of a, plug in the 1, negative 2 over, wait,
It's
oh my goodness, oh my goodness, oh my goodness. We should sue.
No.
Where's my coffee?
You're
I
good.
need to finish my coffee. Yesterday I thought it was Wednesday, it's okay.
Oh, it's Friday today.
It's Friday. We're just playing for the weekend. Alright, so,
I know it's true.
what do we got? Whew, pause, do I plug in B first?
Yeah.
Yes.
Then do I plug in A?
Yeah.
Is it legal?
Yeah.
Is it good?
Yeah.
Does it match?
Yeah.
Let's go. What's negative 2 over square root of 4? Negative 1. What's going to happen to your C's
Cancel.
every time?
Cancel.
So guess what I'm not going to write anymore for definite integrals?
C's.
Forget the C's. They
Fine.
cancel every time. I have to subtract them anyway. What's the point?
Exactly.
Exactly. Minus a negative 2 is? What's going to happen when you plug this integral into your calculator? If it approximates well enough, it'll get 1. If the approximation technique can only get it so close, it'll have point that we will make 1 because we know that's the real answer. It couldn't quite get to because poor calculator, it approximates. Okay. Solved. Done. Good. Area under curve.
No problem.
Let's keep going.
That's the one.
Let's do some more.
Oh, this is not. This is not.
You see how 4, 1, 4, 2, 4, 3 all just got married?
Hey, this literally.
Is it just me, or do you hate it when you get like pi over 2 or something in the? Because it just looks wrong. Because then it's like.
But unit circle, it's not a big deal.
Well, no, not that. But it's like when I do the integral, it's like one continuous line of numbers because the 2 is like too big.
You just have to, well, see, that's why, to be honest, that's why I do my fraction off to the side. I think it looks nicer as far as placement because of that very reason. But some people get confused by that, especially if you have something like pi over 2x. They're like, wait, is it
Is it? Yeah.
pi over 2x or is it pi over 2x, right? So it's a struggle. There's not even a pi over 2. Anyway,
Pull out that 2. Let's go.
pull out the 2. Antiderivative cosine,
Sine.
positive sign, right?
So go backwards. Let's see. Let's see.
Why am I not putting plus c?
Oh,
it cancels
It's
anyway. You're
not
wasting your
indefinite,
life.
it's gonna cancel out, so I'm gonna leave it off. However, if the bounds aren't there, you need the,
So
Let's
basically,
see.
it makes it even
Okay.
easier to forget because once you do definite integrals, then
don't
you go
have
back
to
to
write it
indefinite
down.
integrals. and you
except
have to
definite
actually-
integrals always need to equal a number. So if you can get that established in your head, like definite integrals are always a value, indefinite is always a function. So you can say something like, I don't know, what's our way of remembering it? C is an indefinite integral or something. I don't know. We'll think of something.
Okay.
Kind of like our football.
Alright, let's do this.
Yes. What do you need to know in order to finish this problem?
Your unit circle, but not, I mean,
Funny.
not very
For this one
complicated.
very problem, you need to not only recognize a definite integral, not only recognize a trig function cosine, not only know an anti-differentiation rule and a constant property, not only know the fundamental theorem of calculus to plug in, not only know what subtraction is, but also know your unit circle. Woo! Go team!
Wait.
So we plug in.
Zero.
Because
As long as you know what's what, it's not a beta. Yes, I've been doing too much pre-count. 0 equals. How do you think of it? If you think cheater chart, sine counts up 1, 2, 3, starts at 0, at 0. So that's one way of thinking about it. The other way of thinking about it is on the unit circle. Remember, sine is the y value. The y value at this guy is 0, and the y value at this guy is 0. Or if you think about the sine curve, doesn't he start at 0 and hit again at pi and hit again at 2 pi? Either way, both of those guys are 0, and I end up with a final answer of 0. Wait, why does this make sense?
That's what I mean, because like the area under the top curve and the area under the bottom.
If I was to visualize not the antiderivative, but visualize the original, doesn't cosine look like, isn't he an odd function?
the top.
Isn't he an odd function? With symmetry? He said, careful, the bounds aren't quite. He's an odd function with symmetry, and his symmetry says, hey, if I take the area from, if I was to draw this perfectly, it is cold, right? If I was to take the area between 0 and pi over 2, and take the area from pi over 2 to pi, guys, the area that's above the curve, positive displacement, and the area that's below the curve, negative displacement, they're symmetric. So positive plus and equal negative is always going to equal 0. Question, what other bounds could be there for cosine that would make an area of 0?
2 pi and 0, right?
Yeah, 2 pi and 0 would work, because then you would add more negative, but then you would add more positive. That would cancel and this would cancel.
Well, theoretically, any 2
Give me
pi's
a
that are-
negative left bound.
As long as they're anywhere displaced like the same amount from the inflection point, you should get that, because the inflection
True.
point's at 0.
But also, can anybody give me a negative bound for A? That would, with a positive bound for A, that would give 0?
Negative pi.
Negative 1, negative pi over 2, pi over 2? No? No,
Let's see.
never mind.
Negative pi over 2 would be positive. Positive pi over 2 would be positive. Wait. Okay. How about negative pi to pi?
Plus 1.
Negative pi, well no, that's negative positive, positive negative. Would that work?
You subtract 1 from the left and then add 1 to the right. If you do.
Do you guys see that as soon as I start going negative positive and I'm keeping it symmetric, whatever's on this side will be copied on that side? So for any even function, whatever's here from 0 to pi would be here from negative pi to 0. So I
Also
can
would
just
be
take
0.
this and then double it. For any even function, whatever is here will be doubled on the other side. For any odd function, if I was to take areas of this guy, whatever's here, the opposite is over here. So from negative pi to pi would be 0. From negative 2 pi to 2 pi would be 0. Everything negative to positive would be 0. But for even, it's doubled, which sometimes will be a number and sometimes will be 0. Anyway, let's keep going because our point was to practice. Let us see. Now what?
Oh, shit.
Let's distribute.
Yes. Let's rewrite, yeah?
That'll save you time.
So then the integral, it'll definitely save you time. Why am I going to do x to the 3 halves plus x to the 1 half? I made a jump. Can you follow?
Because, yeah, but now you can simplify.
Because x to the 1 and a half, so 3 halves, yeah? And then x to the 1 half. Good. So then anti-derive, what do we got?
2/5 x 5 halves.
Okay, but just Sean for helping them keep up, I would say x to the 5 halves times 2/5. Because what's the very first thing you have to do? Add 1, right?
And plus 3 halves.
Good, and then plus x to the 3 halves, David, keep going, times,
2/3.
good. 0 to 2. Whether you do a bracket, whether you do a straight line, both ways are acceptable. Kind of depends on my mood as to which one's which. And if there's absolute values, I always do a bracket because otherwise it gets tricky. P.S. We do not know an integration formula for absolute value yet. Just a heads up.
Wait, why'd you erase that too?
Oh. So I was going to erase the bracket and put a straight line. And I was like, no, sometimes I do a bracket. Okay. Who goes in first?
Zero.
Top down, right?
Yes.
Top down. So let's go ahead and wait. I don't like it.
Why not?
It's gross.
It looks disgusting.
It's true.
It's nasty.
Fix her up.
Okay, how are we going to fix her up? Can I be AP-ish for a second? I'm going to be AP-ish for just a second and remind you guys something about anti-derivatives. It's not even necessarily super applicable here, but that's okay. I'm going to pull out a 2/15 x to the 3 halves.
That's a little stretch, but okay.
Whoa, what? That's
No, do you
the
want-
Why did I pull out a 15?
That's the lowest, or the
five and three with 13.
It's the common denominator. So pause.
I get
If
that.
I was to get this to be 15, what would I multiply top and bottom by?
By 3.
So 3 and 5 is 15. It comes out. The 2 comes out, but who's still left inside?
1,
The
3.
3 times, I took away 3 halves, so I just have an x left?
Wait. Oh, yeah.
So if I just.
Because 3 halves and 2 halves is 5 halves.
Yeah.
And then 6/15 is 2/5. What's this guy going to become? To make it 15ths, what would I do? 5 over 5.
So we 10.
15 comes out, the 2 comes out. Well, the 2 comes out though.
5.
So 5, and then didn't I take that guy away?
Yeah.
Oh, that's nice. And then, what is x to the 3 halves? Isn't that x square root of x?
Yes.
Okay. That's easier on my brain. I don't know about you guys.
Yeah.
Then when we go to plug in, I have
That's easier.
2/15 times 2 root 2 times 3 times 2 is 6 plus 5. Now pause. Super common mistake.
Just parentheses around the whole thing. This
Not thinking or being so focused on how much work that was, being so proud of yourself to forget there's still a 0 to plug in.
Oh, that's right.
Oh. But when you plug in 0, what's 2/15 times 0?
0.
No,
Times
they'll all
anything.
cancel out.
5.
So we're lucky on that one.
Oh.
It would be 5, but 5 times 0.
Oh, okay.
But careful, it's not always 0. Not always 0 at all. What do I have left? That's going to be 11. 11 times 4. 44. 44 root 2 over 15. Double check those. 6 plus 5 is 11. 11 times 2 times 2 is 4. 4 times 11 is 44. 44 over 15. Got it. Whew, that was fun. Is the math always super easy? No. So do it step by step. Do it in whatever order or not whatever order. False. Do it however slowly you need to do it. Please don't help your brain.
You should have stopped a step before then.
Okay, guys. Do we have more to do?
No.
Okay,
Homework time.
we're getting there. You guys would be able to accomplish almost everything in homework besides. Oh, we still have one more minute, or are we done? No, we still have 1 more minute. Okay.
No, we're done.
We're gonna skip this guy for a second. Let's go down to this guy.
Oh.
I thought we can't do absolute value.
How do we do absolute value? I just told you a second ago you have no way to do absolute value. At least
There is
no
a formula.
formula. There's not a formula.
Oh, really?
So what do you do?
It's you have to conceptualize.
You ask, what happens when I
You
put
just
the
gotta-
absolute value over a whole function graphically?
You just kind of bump the negative bits.
Whatever's negative
Turns positive.
turns
It looks pretty
positive.
stupid.
Doesn't look great. But whatever's negative becomes positive. Whatever's positive stays the same. Now pause. Where does this switch happen for this guy?
0.
Because he's 0 at his 0 is at 0. So at 0, I need to say 0 in between. Ooh, 0 is in between. So from -1 to 0, I need to say, you know what? Your normal area got flipped. Your normal underneath area got flipped and is now positive. But, you know what? I don't mind you over here. So you get to stay the same. You stay the same, but you, no, you flip. And then what do?
And then you just do it.
Then you solve. Bye, go kids. This section is not done. So therefore, the entire homework is not due until Tuesday. However, you practice those antiderivative, no, definite integrals by hand for Monday. As far as you can, have a number where you got stuck, ready for me. I'll compare it with other students in the class for the spot check, so be ready.
Does that even actually tell, like, which side has been flipped? Because couldn't that just as easily be...
Oh, Angela says hi. Yay, did you guys have fun? Yeah. Where'd you end up going?
We went and got sushi.
Oh, nice. That's a good one.